Bu benimle. Tamam. Özü istəyirsiniz də parası. Bu yan. Güzel. Bunu necə qətləmiyim aparmayla o problem olur.
Orada Xəzər Universiteti Baxıra, baxırdım. Davaq tapşın.
Boş payında.
Yox.
Əgər sualınız var, sonra məndən Azərbaycan dilində soruşa bilərsiniz. Orada olmurdu, çünki orada biraz qulaq asanlar var. Ölkələrdən ona İngilis danışmalıydı.
Orada İngilis danışmalıydı.
Da mən bağışlayım, biraz təmbəllik elədim.
Bölme takdim edin. So next speaker, Professor Shakir Nagiyev, the exact solution of the hyperbolic pöschl-teller potential by functional methods. So please.
Title of this here. This is a quantum mechanical problem. As we know, there is many phenomenological or exact theoretical potentials, quantum potentials in both non-relativistic and relativistic quantum mechanics. Potential models play a key role in studying the physical properties of micro objects. Potential models are based on wave equations, which are fundamental equations of motion of quantum mechanics. As we know, these equations may be Schrödinger equation, Klein ordinary Dirac equation, and there are third equation, finite difference version of relativistic quantum mechanics, which is developed in Dubna group. In many of them are phenomenological, these potentials. For example, Hulten potential, Morse potential, Rosen-Morse potential, Kratzer potential, the trigonometric hyperbolic potential, pöschl-teller potential, Dagale. Many of these interaction potentials have not only many successful applications, but also the other important properties that they are exactly soluble in the framework of non-relativistic and relativistic quantum mechanics for the LS wave. For the in work, Barut et al. Used an algebraic method in the one-dimensional case to exactly solve the Schrödinger equation for the pöschl-teller hyperbolic potential, and found both discrete and continuous spectrum, bound state and scattering wave functions. Here the parameters A and B are relevant to the potential depths, while real positive parameter method describes the range of the potential. For a special case, A is equal 0 was this problem solved before in papers. Hyperbolic pöschl-teller potential is an important diatomic molecular potential. This potential has been carried out widely in the quantum physics. Our main goal is this potential has not been solved by direct methods. Hyperbolic partial. Our main goal is to solve exactly one-dimensional Schrödinger equation with a hyperbolic pöschl-teller potential. This potential is here. In this regard, we also note that in a recent paper, the authors constructed two exactly solvable semi-infinite and infinite models of a singular one-dimensional quantum oscillator with coordinate-dependent masses within the framework of non-relativist quantum mechanics. The first model is a singular oscillator corresponding to the following mass, and the second model corresponds to the following mass. Another goal of our work is to show that the hyperbolic pöschl-teller potential well problem is equivalent to the first model, but the trigonometric pöschl-teller potential well problem is equal to the second model of the linear singular oscillator. Schrödinger equation for the hyperbolic pöschl-teller potential has the form. Here, B and I satisfy these conditions. We obtain only continuous. In other cases, we obtain only, we will solve the equation in case. In this regard, we note that potential has a minimum at this value. This is the depth of the pöschl-teller potential well. The function has 0 at point. We rewrite the wave function psi in the form by next defining epsilon h3 a prime b prime. One obtains from the above an equation for p. This equation, since potential satisfies the following limit relations, and for E is less than 0, the energy spectrum will be discrete, and for E0 will be continuous. Let us consider this case separately. Discrete spectrum bound state solutions. In terms of variable, T is sinus hyperbolic square alpha x. The equation takes the form, differential equation. Here, these parameters has the form from these functions, T, sigma, C2, C1. We seek the solution of equation today in the form. In this form, from the condition of square integrability, follows that the parameters A and B satisfy these conditions. A is greater than 0, therefore P is After some simple calculations for that function, we obtain the following equation. Following differential equation. Here, the parameters are the following. The parameters A, B are arbitrary for now. We will now choose them so that the condition holds where lambda is constant. From these conditions, we obtain the following equalities. First, from the equality, use 0, we find parameter A, and then from the equality, we find the parameter B. We have the results. Or taken into account 2.10, we find A and B parameters. For lambda, we choose the expression. As a result, for the function, we obtain an equation of the hypergeometric type. Let us find a polynomial solution of this equation in two ways. First way, in the equation we make change of variable. T is minus z. Z is sinus square alpha x. Then we get this equation. Let us now compare the equation with the hypergeometric equation. The general solution of equation is written as where gamma 1 are non-equal 0, minus 1, minus 2. Comparison of equations leads to the following equalities. Since E is negative, then chi is positive. In terms of potential parameters, alpha 1, beta 1, gamma 1, we have the expressions. Since in our case, 1 minus gamma 1 is negative, the second term in diverges at z is equal 0. Therefore, it must be C2 is equal 0. Thus, for the solution of the equation, we obtain the result. Or, in order for the function to be a polynomial of degree n, we must set alpha 1 is minus n. N is now an integer number. This is the second condition of energy condensation. From this we obtain that energy levels of the system under consideration are determined by the formula. Here, there is a finite number of energy levels determined by the condition. Is here. Thus, the desired polynomial solution will. Thus, the desired polynomial solution will have the form. Taking into account these formulas, we find that wave functions corresponding to the energy levels are in the form, can be written in the form. Note that the condition ensures the square integrability of the wave function. Second way, in equation in this equation, we make a change of variable. T is equal xc minus 1 half, where xc is here. Then we get the equation for the dy. Let us compare this equation. We can compare this equation with the equation for the Jacobi polynomials. Is from the comparison we find that we find these conditions. Note that in this book, mistake was from the comparison we find that alpha 2, beta 2, and lambda and yn in terms of Jacobi polynomials. This function is expressed in terms of Jacobi polynomials. we can express the wave functions using full wave functions as here the normalization condition has the form. This is discrete spectrum, the case discrete spectrum. We can also we consider also the continuous spectrum, scattering state solutions. The spectrum of positive agent values of the energy of the system under consideration is continuous and extended from 0 to infinity. We now turn to solve equation for continuous spectrum. Similarly, we make the same variable. Quantities alpha 1, beta 1, k defined by the formula are now complex, as shown here. For the scattering status, energy is positive and the kappa is positive. As a result, we can get the wave function of the scattering status as where C is a normalization constant. For the wave function, we have the condition. Let us study its asymptotic expression for large x. To this end, using the recursion relation of the hypergeometric function. This asymptotic formula. We have this asymptotics. And by setting D is, we have this asymptotic relation. By comparison, this formula with the general boundary condition of the wave functions normalized by the delta function of P, the momentum of the particle at infinity, we can find normalization constant. At the end of this section, we note that we obtain the reflection and transmission coefficients as reflection coefficient is 1 and T is 0. That is due to the infinite potential wall at the point x0. The particle is completely reflected from the wall. Hyperbolic pöschl-teller potential well as a model of the singular oscillator with position-dependent mass. In this section, we will show that the hyperbolic pöschl-teller potential well can be considered as a model of a singular oscillator model with coordinate-dependent mass proposed in work 9. To do this, it is sufficient to verify that Schrödinger equation describing these models coincide in the form after the transformations. For example, we transform Schrödinger equation for the singular oscillator for the model of a singular oscillator with mass mx and potential. This potential. This is singular one-dimensional singular oscillator. This is easy to do if we pass to a new variable. Then we obtain an equation that coincides in form with the equation with pöschl-teller potential. Where the following quantities are analogous to the analogy of the parameter will be here as shown. Using this analogy, we can find the energy spectrum and the wave function for the singular oscillator model. As an example, we derive from formulas and the discrete energy spectrum. We easily obtain the energy spectrum. And for the second model, in the same way, we can analyze and we can easily find the explicit form of the wave function of the singular oscillator model. I want to say that pöschl-teller potential for the hyperbolic position not be solved by direct. Another goal is to apply this equation for the spectrum for molecular spectrum. But this is hala başlamamış. Yarım çıktım. It is ya ben kurtardım beni.
Is there any questions? Sorunuz var mı? So, as I understand from your talk, the potential plus pöschl-teller potential and plus harmonic oscillator operator together with this model is equivalent to harmonic oscillator model with position dependent mass. Is this true? Yani pöschl-teller potansiyeliyle harmonik osilatora ilave etsek potansiyelleri, bu harmonik osilatörda kütlenin koordinattan asılı olması modeline ekvivalent.
Bu İngilizce dedik, İngilizce değil ben diyebilirim.
Okay, thank you. So let's thank speaker again.